Okay, so let us start the today's lecture. In this this is the fourth session of NPTEL PMRF live session on computer networks and internet protocol. In this, we will talk about other services provided by transport layer. First, we will talk about the transport layer performance. That is how the end-to-end connectivity has been done and how the performance for end-to-end connection is measured in the transport layer. So in this lecture, we'll first cover the broad analysis of week 4, that is the major pointers which have been taught in week 4. And then we will discuss a few assignments which are related to today's lecture and the past assignment which have already been provided the solutions with. So what is the bandwidth delay product? So whenever there is one host and another host communicating between each is which wants to communicate with one another. So we need to compute the bandwidth delay product, or what is the channel capacity of that particular link. So the bandwidth delay product is measured by this product of link bandwidth and into the link delay. So this link bandwidth is the bandwidth of the link. That means if we represent it in the cross-sectional area, so for example, this is host A, okay, and this is host B, and A wants to communicate with B through a pipe. So this cross-sectional area will be the bandwidth, link bandwidth, that how much input in the cross-sectional area it can give, and this the total time taken over this route is the link delay. Okay, so in this manner, we compute the bandwidth delay product, which is the link bandwidth into link delay, which is an important metric for the flow control. That means how much maximum data or the flow which is possible when A wants to communicate with B. For example, in this, consider the bandwidth here 50 kbps, and what is this? Yeah. So consider a bandwidth here of 50 kbps, and it is a one-way transit time with a delay of 250 milliseconds. So the bandwidth delay product will be the product of this bandwidth into the transit time. That means the delay. That gives us 50 into 250. That is 12.5 kilobits in all. That is the bandwidth product. So that means assume that 1000 bit segment size. So BDP allows 12.5 segments to be transmitted over that particular link. That in the so I'll explain how does that mean. So for I mentioned here like this was the link, and this was another. I mean, this was host 1 and this is host 2, and they want to communicate with each other using a pipe. So if their bandwidth delay product is 12.5 kilobit, this is 12.5 kilobit. So you want to transmit a segment from 1 to 2. Okay. So if a segment size is 1000 bit per segment, so how many segments will you be able to transmit? That will be 12.5 segments. So this bandwidth delay product defines the channel capacity or the link capacity. So consider the event of a segment transmission and the corresponding acknowledgement reception. This counts to be a round trip time. That means whenever host 1 communicates with host 2, so it sends the segments and receive back the acknowledgement. These are the data, and data, and this is the acknowledgement that we receive back. So when this data is transmitted, at this time the now the this divide this has the bandwidth product of 12.5, then this again has the bandwidth product of 12.5. So if the total we have transmitted 12.5 segments, then we can also receive 12.5 segments acknowledgement corresponding to that. So in all, the for the overall channel, it is possible to transmit 12.5 into 2, that is 25 segments in all. That means 12.5 of data and 12.5 of acknowledgement. So this the complete time which takes from 1 to 2 and back to 1, that is called the round trip time. This is twice the one-way latency. These are the few metrics which are important in terms of this transport layer. So I hope this is clear to everyone. So what is the implication of bandwidth delay product on the window size? So the maximum number of segments that can be outstanding within this duration, as we talked, it was 25. That means for the incoming link and the outgoing link. That means here, as I show, as I've already shown, from 1 to 2, and then from back 2 to 1. So these combine to be 25 segments. However, there is one plus one here, as mentioned here as one, which is the acknowledgement which is sent only when the first segment is received. So that is the extra acknowledgement with the help of which the next corresponding packet is move into the outstanding segments in from 1 to 2. So a total of 26 outstanding segments are possible in a channel. So this gives the maximum link utilization when host 1 wants to communicate with host 2. That means the link will always be busy in transmitting data segments. So here these are the terminologies that BD denotes the number of frames equivalent to BDP, and W is the maximum window size. So the window size here possibly can be 2 times BD plus 1, which gives the maximum link utilization. So this is a very important concept to decide the window size for a window-based flow control mechanism. For example, if you have been given the parameters, say the bandwidth, product, and the link utilization and everything, so then you have to decide which protocol will be more suitable for this type of metric. So then that you have to decide with the possible maximum window size which can be allowed to communicate for that link utilization. So how it is related to the protocol decision choice as we were discussing now. So for example, consider the link bandwidth equals to 1 Mbps and the delay latency equals to 1 millisecond. So consider a network where segment size is 1 kilobyte, that means 1024 bytes. So which protocol is better for the flow control? So first approach will be to compute this bandwidth delay product. So when we compute this BDP, that is bandwidth into the latency, which gives out to be 1 KB, that is 1024 bits. The segment size is 8 times larger than the BDP. That means the link cannot hold an entire segment completely. So the segment size is too much larger. So here the sliding window protocols do not improve the performance as we cannot transfer the data even in a parallel mode. So in this case, stop and wait protocol is the better protocol in which you send a single piece of segment and then receive its acknowledgement and then sends the corresponding segments. This offers a very less complexity. So now we will solve a certain questions similar to this. So assume that in a and wait ARQ system, the bandwidth of the data line is 1 Mbps and 1 bit takes 20 milliseconds to make a round trip. So you have to find the bandwidth delay product first and the utilization percentage of that link respectively if the system data frames are 1000 bits in length. I hope everyone is clear with the question and I'll give you some time, 5 minutes. You can make a try to solve that question. If any one of you gets the answer, please put up in the chat. Yeah, so this is the question. Please thoroughly read it and try to solve it, and then I'll share the solution in details and give a solution how to solve. Did anyone able to solve that question? Is anyone interested in the solution or is able to give the answer? Please write in the chat once or raise your hand. Anything will do. Okay, so the solution is that the bandwidth is 1 Mbps, that is 1 into 10 to the power 6 bits per second. Then the delay, it's as it is mentioned, the one bit takes 20 milliseconds to make a round trip. That is 20 into 10 to the power 3 seconds. So the bandwidth delay product will be bandwidth into the delay, that is 20,000 bits. So the system can send 20,000 bits during the time it takes for the data to go from the sender to the receiver and back again. However, the system can send only 1,000 bits, as it is mentioned that the system data frames are 1,000 bits in length. So the utilization is equivalent to 1,000 divided by 20,000, that is 5%. This is another question. I hope any one of you can respond if it is clear to you or not clear to you. Are you all able to access the chat, or is there any glitch in between? Oh, you are able to access the chat. Then it will be good if all of you please respond as well. So in a stop and wait ARQ, we have studied the stop and wait in the last week. Bandwidth delay product is 20,000 bits. Given the frame size is 1,000 bits, what is the percentage of utilization of link if we have a protocol that can send 15 frames without waiting for acknowledgement? You're given a bandwidth delay product and you're given the frame size as well. What is the percentage of utilization of the link such that the protocol can send 15 frames without waiting for the acknowledgement? Did anyone got the answer? Zero 0.75. Okay. So the bandwidth delay product is the bandwidth into the round trip time, that is the delay time over that channel. And so round trip time is 2 times the single length of that latency, single side latency. So here it is given that bandwidth into round trip time is 2000 bits, and the protocol is sending 15 frames of 1000 bits, that means 15,000 bits. Utilization will be directly the 15,000 divided by 20,000 into 100, that is 75%. So yes, it is correct. I hope everyone got it. So now we will see how the application and transport layer interfacing is done from the sender side and the receiver side. How do they communicate with each other? So the application layer is the application is implemented at the user interface, and the transport layer is implemented at the kernel side. This I think everybody knows. Okay, so now the application at the user end first sends the write and send request, that is the commands. In this manner, it tries to send the information that it wants to send or the data it wants to send. And so that data is then sent to a destination port for the identification at which port in the transport layer it wants to communicate with. So here the TP port sent will decide that the port at which the transport in which at the transport layer the application wants to communicate. So the data which is sent through the write command is not necessary that all the data which the amount of data which has been sent from the application layer is not necessarily that the same data has been sent over the transport layer. So the buffer size may varies, or the link bandwidth may varies. So for that purpose, they maintain a transport buffer at the sender side in which the data which is able to be received from the sender side, that is only sent, and the other data, or if there are multiple write requests, that data has been stored in the transport buffer at the sender side. So at that time, the write call blocks the port until the complete data is written in the transport buffer. So if that data, quantity of that data is more than the size of the transport layer buffer, so then the write call gets blocked. Similarly, at the receiver end, when the T-port receiver receives the data from the particular IP, so then it identifies to which transport layer port it wants to send the particular data. So it might be necessary, not necessary that it might be the case that the application coming from the data coming from one application might be suitable for a particular type of port only. So it needs to go to this port 2, but not to port 1. For example, it needs to go to this port 2, but not to port 1. So firstly, it identifies on which port the data will be received at the receiver end, and then stores that data in the check buffer. So if the read call is made at the receiver end to read the data, and the receive call gets blocked and blocks the port until the data is received and the complete data is read from the transport buffer. So that there might be a case that the transport buffer is empty at a certain time when there is no data written from the sender side. So at that time, the read call also blocks the port at the receiver end until the data is received and the complete data is read finally from the transport buffer. So this is the way the control is possible, that we have the IP address at the network layer, then we have the transport buffer at the transport layer, and then the data is read by the application layer. So there can be the rate difference between the rate of application read and the rate of transport receive, as we talked just right now, that it might be the case that the sender rate is different and the receiver's rate is different. So for that purpose, a transport buffer is maintained in which the data is stored, and whenever there is a read call, then it reads the data, and whenever there is a write call, then it writes the data. So there might be a case that buffer size may be smaller for certain application, but the buffer size is needed much larger in case of other application. However, if we keep the maximum buffer size very large, so there might be a space which may be left empty, and that leads to overhead. So for that, we need to have a dynamic buffer management for the window-based flow control. So here the sender and receiver needs to dynamically adjust the buffer allocation. So based on the rate difference between the transport entity and the application, the available size of the receiver buffer changes. So for example, here are the segments which are waiting at the buffer end, and these are the segments which are read by the application. So we still have this free space at the receiver buffer. So sender, this receiver space is a overhead which should not be there. So the sender should not send more data compared to the receiver buffer space. So the sender can send this much of data in the free space which is left. However, it cannot send more data than that. So it needs to dynamically adjust the window size based on the availability of receiver's buffer space. So if the receiver buffer space is available, so the sender's window size will be adjusted according to the availability of the buffer space. For example, if the receiver buffer space available is seven seven segments, then the sender window size can be 7 segments. Otherwise, not. So here is the flow case example, how the dynamic buffer management for window based flow control is possible. So first, the sender, that is A, sends the request for 8 buffers. So A wants 8 buffers. Then the B grants message that it has only, that is B is the receiver side, it has only 0 to 3 buffer spaces only. So it gives the acknowledgement of sequence number 15, and with the buffer size equals to 4. Then the sender side A sends the sequence number 0 with data M0. Then A has 3 buffers left now. Then it sends with sequence 1. Then A has 2 buffers left now. Then it sends with sequence 2, and A has 1 buffer left now. But it might be a case that this message gets lost, but A still thinks that it has 1 buffer. So now B acknowledges with the receival of 0 and 1, and it sends that acknowledgement 1. That means that 0 till 1, all the packets are received. So it permits 2 to 4. That means the buffer space is 3 now. That 1 was this, which A thinks only 1 is left, but there are 2 left, and Now, yeah, A thinks only one is left, and now it acknowledges with the two, and two other are also left. So it has allotted three buffer space. So now at the seventh point, it again sends a sequence number 3 with data M3. So A has one buffer left. Then it again sends sequence 4 with data M4. Then A has 0 buffer left, and it must stops. But it sends the data. So the A times out because there is no receival of that buffer, and it retransmits that data because it does not receive acknowledgement for the 2. So now the receiver end will acknowledge 4 and says the buffer space is 0. Then again it acknowledges 4, but it says the buffer space is 1 because the data is now received and the buffer is empty. Then like this way the flow continues. Okay, anyone is having any doubt till here? So there might be a case of a potential deadlock in case that the host B has sent the acknowledgement and there is a buffer space of 4. However, on receival of host A, that gets lost. So the host A thinks that the B has not sent the message, and B thinks I send the message, but A is not sending back any kind of messages. But this thing makes a potential deadlock, and you cannot come out of it. So next we'll talk about the congestion control in the transport layer network. So here we see that firstly there is a flow from A to B in which A wants to communicate to B with a flow of 1 Mbps. Okay, so the whole there is no other flow coming. So the whole allocation has been allotted to A. This is one. Then another flow comes into picture in which flow 2 starts with the same 1 Mbps to B. However, this flow cannot be managed from flow 1 and flow 2. So they divide amongst each other and allot 0.5 Mbps flow to flow 1 and flow 2 each. Then again at time interval 4, there comes another flow with a very less flow amount, that is let's say 10 kbps. Okay, so that is very less. So that flow 3 has been allocated this 10 Mbps, and the flow for flow 1 and flow 2 has been dropped a bit. So this at timestamp 9, as you see, a certain flow, that is flow 3 stops. So the and the flow 2 stops, not the flow 3 stops. The flow 2 stops. So the allocated bandwidth for flow 2 also is gained by this flow 1, and it attains a higher bandwidth. So this is how the changing bandwidth allocation is allocated over time. However, it might lead to congestion when there are multiple flows over the same channel with different bandwidth. So how to control this congestion, and this will lead to congestion as the bandwidth is very low for the individual flow. So how to control this congestion, that we see in the subsequent slides. So the flow enter and exit network dynamically. So applying an algorithm for congestion control is very difficult. So the rather than to control the congestion, we do a congestion avoidance, which regulates the sending rate based on what the network can support. That means when the congestion has been occurred, then it avoids the congestion at a certain basis. After occurring of the congestion, how to dynamically allocate is difficult. But before the congestion is occurring, or there is a state when you see the congestion has been occurred, you can avoid the congestion by congestion avoidance algorithm, in which you regulate the sending rate based on what the network can support. So the sending rate is equivalent to minimum of what is the network rate and what is the receiver rate. So here the network rate is the gradual increase of the network rate and observe the effect of flow rates. That means if there is a gradual increase in the network rate and it observes the packet loss, so that means the congestion will occur. And the receiver rate, which comes from the flow control, that means the receiver advertise the window size for the sliding window flow control. So minimum of the two, that is the network rate or the receiver rate, decides the sender's rate. So we see what is the impact over the good put and the delay when there is a network congestion. Now you see there is this network capacity, and the normal pattern is that in this way it's increasing, the offered load or the packets are increasing. But there might be a case that the packet get lost, or there is a possibility of congestion and then the packet gets lost, and there, at that time the good put of the system reduces, the network reduces. So this is the delay process in the similar manner, that this was the delay initially. So when the packets gets lost or there is a congestion, so the delay increases significantly. So the congestion control ensures that the rate of all the flows in the network is controlled in a fair way. A bad congestion control algorithm may affect the fairness. Some flows may get starved. And hard fairness in a decentralized network is also difficult to implement. So the best possible approach that is followed for the congestion control is max-min fairness, which is an allocation is a max-min fair if the bandwidth given to one flow cannot be increased without decreasing the bandwidth given to another flow with an allocation. As we have seen in the previous example, that if a flow 1 is moving in this way and a flow 2 comes with a similar bandwidth, so we decrease the bandwidth of flow 1 and increase the bandwidth of flow 2 to a similar pace, so that the equivalent distribution of bandwidth is given to both the flows. That means it should be max minimum fairness. That means the maximum bandwidth flow should be dropped and the minimum bandwidth flow should be increased. So now we see if we want to communicate from how the two interfacing from host 1 to host 2 takes place with application and the network layer when there is a transport entity in between. That means the end-to-end communication. So the host 1 wants to communicate with host 2 using the application or the session layer. So first it provides the port number for at the application and a transport interface, so that it finds at which port of the host 2 it wants to communicate. Then to identify the particular network ID at which network it wants to communicate, or a particular machine at which it wants to communicate. So the transport and network interface offers the IP address. So in this way, the transport layer applies the interfacing with the application and the network layer. So once we have identified the exact port to which it needs to send and the IP address of the machine of that is the host 2, then we create a logical pipe between the sender and the receiver on the transport layer, which monitors the data transmission through the pipe. So through this pipe only, we are able to send the segments from the transport layer using transport protocol. To allow users to access transport service, there are the transport layer must provide some operations to application programs. So the major primitives that the services that the transport layer offers is the similar in which we talked about the connection is established. That is, first it listens, that in which it blocks until some process tries to connect. So if a process is in listen state, then only another, if one machine is in listen state, then only the another machine, that is the client side, can send to the server that should be in the listen state. Then there is a connect primitive in which allows the connection request, that is the packet sent, which means that actively attempt to establish a connection. So after the connection is established, it uses a primitive send, which sends the data packet or sends the information. And then there is a receive request in which it blocks until the data packet arrives at the receiver side. Then this is a disconnect request in which the packet send is disconnection request, and it requests to release the particular connection. So the transport layer needs to remember the state of the pipe so that the appropriate actions can be taken. We need a stateful protocol for the transport layer. So this is the state diagram of the transport layer protocol. Here you can see this dashed lines are the sender side, and this blocked line is the client side. So initially it is idle. Then it wants to it sends the connect primitive, which is executed at the client side for the active establishment through the sender side, the server side. So then there is this connection request has been sent from the client side, that is received at the server side. Then the passive establishment is pending. So the server side sends the connect primitive, and this is the client side accepted that segment of the connection, and then the connection is established. So in the similar manner, whenever the established connection wants to get disconnected, so disconnect primitive is sent from the client side for active disconnection which is pending. Then the disconnection request segment has been received at the sender side. Here the passive disconnect request is again pending. Then the sender side sends the disconnect primitive to the client side, and the client side receives the disconnect request segment, and then the connection is disconnected and becomes idle again. So this is how the state diagram proceeds from the client to server connection and disconnection. Anyone having doubt till here, or is it clear to everyone till now? So what are the difference? Till now we have used all the terminologies. So there are three different terms, that is the frame, segment and the packet or the datagram. So the segment is the term which we use in transport layer. Then we add the segment header, that is the transport header to it. Then it forms the packet. That packet is used in the network layer, and that is the packet. The packet header is added to it, which forms the frame, which is used in the data link layer, and then the frame header is added to it. So the segment is used in the transport layer, packet is used in the network layer, and frame is used in the data link layer. So, transport layer process flows. So, firstly, it is the connection establishment, as I mentioned. It initiate a connection by selecting the initial sequence numbers, ensuring that the initial sequence numbers do not fall within the forbidden region of the previous connection between the same connection. So, I think every one of you remembers what is the forbidden region. So, this region when we have the sequence number selected, and it is this at this time the connection disrupts. So this is the kind of forbidden region that is followed, because if we start a connection at another time from here, so there might be some overlap due to extreme flow, fast flow, or the slow flow of this next one. So this is the complete forbidden region. So the better opportunity is to start the process after a certain time interval and choose this as a new sequence number. So next is the flow control and the reliability. For that purpose, use the ARQ protocols that we have studied, that is the stop and wait and the sliding window protocol, for ensuring the flow control and the reliability. So here sender will not send data at rate higher than the receiver rate, and sequence number are used to uniquely identify each byte or each packet. And there is a loss in the communication path which is handled through retransmission. So then there is the congestion control, which reduces the transmission rate once the congestion is detected. It helps to improve the performance for end-to-end data delivery. Then final is the connection closure, which close the connection when the data transmission is complete. This is for the synchronous closure with timeout. Now we study the transmission control protocol, that is the TCP protocol of the transport layer. This is the last part that we'll be studying today. So I think everyone is clear till here as well. So TCP was specially designed to provide a reliable end-to-end byte stream over an unreliable internetwork that we have already studied. So what is internetwork? That is, different parts may have widely different topologies, bandwidth, delays, packet sizes, and other parameters. So because of which some packets get lost. So that is controlled by TCP to provide a reliable end-to-end byte stream. The TCP dynamically adapts to properties of the internetwork and is robust in the face of many kinds of failure. So the first TCP was implemented as RFC, request for connection 793, that is the base protocol, and then there were further modification of the base protocol in terms of other RFCs as well. So all TCP connections are fully duplex and point to point. That is, it is a two-way connection. So TCP does not support multicasting or broadcasting. It sends from host A to host B and then receive from host B to host A. So TCP uses sockets to define an end-to-end connection. That is the source IP, the source port, source initial sequence number, destination IP, destination port, and destination initial sequence number. So this is the socket which is needed by the TCP to define an end-to-end connection. So TCP connection is a byte stream, not a message stream. So the byte streams are sent from host A to host B, and the message boundaries are not preserved end to end. So for example, when we are sending a byte stream, say from 100 bytes to 200 bytes, then we are sending another byte stream from 200 bytes to 250 bytes. Then we are sending another byte stream from 250 bytes to 400 bytes. So these are the byte streams which are being sent for a TCP service model. However, there might be a case that these two segments are dropped with 200 to 400 byte streams. However, the segment with 100 to 200 byte streams have been received with host B. So these two segments are dropped. So byte 200 to 400 needs to be retransmitted again. So that might be a case that it is not retransmitted in the similar manner as, as in a similar segment of bytes as it was initially sent. That means 200 to 250 and then 250 to 400. However, it now splits the segment as 200 to 300 bytes and then 300 to 400 bytes. So this message boundaries are not preserved end to end. That was the purpose of this TCP message boundaries, that if a segment is lost, so the message boundaries may be changing depending upon another segment. So now we'll see the TCP protocol, that is the header of the TCP protocol. So this is the 32-bit header, which has the source port and the destination port. Then there is the sequence number, which is again 32 bits. Then the acknowledgement number, that is 32 bits. Then we have the TCP header, that is of 20 bits. Then we have some other this options for the uh, pointers. Then we have the window size of 16 bits. Then this is a checksum for checking the correctness of the message or the segment. Then this is an urgent pointer if we need to urgent send the window size or urgent send the data packet. Then there are some other options from 0 to 32 bits. And there is this data which is optional along with whatever message we are sending. So this is the typical layout of the header of the TCP protocol. So 32 bits sequence number and 32 bits acknowledgement number, as we have already seen. So every byte on a TCP connection has its own 32-bit sequence number, a byte stream oriented connection. The TCP uses sliding window based flow control. The acknowledgement number contains next expected byte in order. That means if we send a byte with the number of 200, then the acknowledgement will be 201. that means the next byte needs to be sent is 201. This which acknowledge the cumulative bytes that has been received by the receiver. For example, if we send a byte from 200 to 400, then the acknowledgement will be of 401. So that is the cumulative acknowledgement that the bytes from 200 to 400 have been already received. So acknowledgement number 31245 means that the receiver has correctly received up to 31244 bytes and expecting the byte 31245. So the sending and receiving TCP entities exchange data in the form of segments. So a TCP segments consists of a fixed 20 byte header plus an optional part followed by 0 or more data bytes. So TCP can accumulate data from several write calls into one segment and split data from one write call into multiple segments. So the segment size is restricted by two parameters, that is the IP payload, which is of the size 65515 bytes, and that is then the maximum transmission unit of the link, that is the MTU of the link. So this, as we have already seen how a connection is built. So now we see how the TCP segment is created. So the write calls from the application writes the data to the TCP sender buffer. So the sender maintains a dynamic window size based on the flow and congestion control algorithm, and then it sends the segment to another network of the host. So the modern implementations of TCP uses the path MTU discovery to determine the MTU of the end-to-end path, uses ICMP protocol and sets up the maximum segment size during that connection establishment. It may depend on other parameters such as the buffer implementation. Here it checks the sender window after receiving an acknowledgement. If the window size is less than MSS, it constructs a single segment, otherwise construct multiple segments, each equals to MSS. So the challenges in TCP design is that segments are constructed dynamically. So retransmissions do not guarantee the retransmission of the same segment. So retransmission may contain additional data or less data. So another challenge is that the segments may arrive out of order, as TCP receiver should handle out of order segments in a proper way so that the data wastage is minimized. So if we want to maintain a TCP connection establishment, then how to choose the initial sequence number? For that purpose, we need to avoid delay duplicates. Do now generate the initial sequence number for every connection from 0. So original implementation of TCP uses a clock-based approach, that the clock is ticked every 4 microseconds, and then the value of that clock cycles are from 0 to 2 to the power 32 minus 1, as we have 32 bits for the sequence number. So the value of the clock gives the initial sequence number. So here, if we have the clock for this particular sequence number and it is disrupted and we want to choose the next sequence number, then we say that the next clock tick defines the next sequence number. So how the host 1 communicates with the host 2, as you can see, it sends this SYN, that is the synchronization message, to host B with the sequence number equivalent to X. Then the host message, host B sends the synchronization that the connection is established and the acknowledgement with the sequence Y and the acknowledgement or with the next sequence number to the host A. Then the host A sends the acknowledgement with the next sequence number, that is X plus 1, and the acknowledgement that it wants to receive Y plus 1. This is how connection establishment is done. And then we choose the sequence number if the connection is lost based on the clock ticking. However, there might be a possible case that this clock ticking is being attacked by the other users if they know that the next clock tick will be the next sequence number. So that there can be a SYN flood attack. Like the multiple clients can send the similar SYN request to the host P at the similar time with the similar clock. So then the host P will be confused that which is the original host A request. So the solution here is to use a cryptographic function to generate the sequence numbers. Now we see how the TCP connection release is done. It is done in the similar manner that it sends the fin request, that is finished, and with the sequence number n and acknowledgement n. Then this is the active close. That means this is the last packet that has been sent from the host A to host B. Then host B is a passive close. That means there are there might be a case when there are multiple packets that needs to be sent from the host B. So at this time, it sends the acknowledgement at the finish and the finished request. So the host A waits till the timeout, and if there are some other packets left for the receiver, and then sends the acknowledgement back to host B. Thank you. So this was the whole lecture. If anyone has any doubt in this lecture, you can ask. I am waiting here. Then we'll discuss few assignments. Okay, so let us discuss the assignments then. So last about this last week assignment, consider this sliding window protocol. The packet sequence is 4-bit long. So what will be the maximum window size is in the sliding window protocol? Case study relevant to this topic. Can you elaborate like what exactly do you mean to say? So the maximum window size is here 2 to the power n minus 1. That is 2 to the power 4 minus 1. That is 15 is the maximum window size. Next question is, flow control is primarily implemented in application layer, session layer, transport layer, or physical layer. So the flow control is mainly a function of transport layer that we already know. And primarily, secondly, it is also been implemented in the data link layer as well. So consider the following statements and choose the correct option. Self-clocking ensures that no two packets in a network have the same sequence number. And second, TCP uses self-clocking. Both the statements are correct. Self-clocking is the mechanism to adjust inter-packet transmission duration based on the sequences acknowledged. It ensures that no two packets in the network has the same sequence number. This mechanism is used in TCP. Which statement is true for go back N ARQ protocol? All segments from 0 to N are retransmitted if segment N is lost. All segments from 1 to N are retransmitted if the segment N is lost. All segments from 0 to N minus 1 are retransmitted if the segment N is lost. Or all segments from 1 to N are retransmitted if N is lost. Yeah, that's right, 0 to N. So next question is, in sliding window protocol, if sender window is made 10, then how many frames would be in the window after transmitting 10 frames? So the answer is 0. If a sender window size is set to 10, then the sender can transmit up to 10 frames without receiving any acknowledgement. After transmitting 10 frames, the number of frames in the window would be 0. So if an application requires reliable communication, which transport layer protocol would it use? ARP, RARP, TCP, or UDP? So the correct answer is TCP. Applications that require transport protocol to provide reliable data delivery use TCP because it verifies the data is delivered across the network accurately and in the proper sequence. TCP is reliable, connection oriented, and byte stream protocol. Which statement is true? Is this the delayed duplicate problem can be solved using two-way TCP handshaking method? Is this true or false? This is false, that the two-way handshake does not solve this purpose. A three-way handshake process solves the problem of delayed duplicate. So what is the maximum size of sender and receiver window in stop and wait protocol? In stop and wait, what is the maximum size of the window? Yeah, right, that's one. So consider the following statements concerning to the selective repeat protocol and choose the correct option. First one, only the lost or error frames are retransmitted. Second, the retransmitted frames are always received in sequence. So the answer is in A. In selective repeat ARQ, only the lost or error frames are retransmitted, whereas correct frames are received and buffered. The retransmitted frames is received out of order. In Unix operating system, the transport layer protocol are implemented as a part of. So it is kernel here, which the transport layer protocols are implemented as a part of kernel. So now we will see another assignment, which is a similar type of assignment which may be given to you this week. So you can check here. So what is the most popular port for establishing HTTPD, that is Apache HTTP server connection? Yes, so the answer is D. C, that is 80, port 80. In AIMD algorithm, that is for the congestion avoidance algorithm. So what is the sending rate WT at the next time interval t plus 1 is increased by an additive factor A greater than 0 when congestion is detected. True or false? Yes, you are correct. So it is the answer is false. That is in AMD congestion is not detected. W T1 is equals to WT plus A. So let the maximum TCP payload be 1450 bytes. Then what is the maximum network layer payload in bytes? Anyone? So the TCP header size is 20 bytes. So the maximum network payload can be maximum TCP payload plus TCP header, that is 1470 bytes. Yeah, you're right. So the service model, TCP service model supports broadcasting. Is it true or false? So that is false. It does not provide broadcasting or multicasting. So which of these statements are true for the transport layer? The transport layer protocol should be stateful. Second, uses FTP protocols for ensuring flow control. Answer is A, that only one is true. Transport layer protocol should be stateful. It needs to remember the state of the pipe so that the appropriate actions can be taken. We need a stateful protocol for transport layer. Moreover, ARQ protocols are used to ensure flow control. The TCP header sizes, which one of these? No, you're wrong. It's not 20 bits. The answer is D, that is 160 bits. TCP header size is 20 bytes. That is equivalent to 20 into 8 bits. That is 160 bits. It is not 20 bits. So there is difference between bytes and bits. Okay. So if it is bytes, then you have to convert it into bits as the question asks. The use of cryptographic function to generate sequence numbers for TCP connection is helpful to avoid TCP congestion overflow, denial of service attack, TCP SYN flood attack, or none of these. This is C, that is TCP SYN flood attacks can be prevented by generating sequence numbers using cryptographic function. For effective congestion avoidance, the sending rate of the network should be minimum of network rate, comma, receiver rate. True or false? So answer is true. So next question is, what are the parameters responsible for restricting TCP segment size? IP address, IP payload, maximum transmission unit, or acknowledgement number field size? Answer is B and C, that the TCP segment size is restricted by two parameters, that is the IP load and the maximum transmission unit of the link. So next last question is that, consider a network with link bandwidth equals to 1 Mbps, delay equals to 1 milliseconds, then the segment size is 1 KB, that is 1024 bytes. Which of the following relationship between BDP and segment size holds? So the correct answer is BDP equals to 1 Mbps into 1 millisecond, which will be 1 kilobit, and the segment size is 1 kilobyte. That means 8 into 1 KB, that is 8 times BDP. So the relation this holds. So yeah, we have completed the assignments as well. So if you have any further questions or any clarifications, then you can ask. Otherwise, uh, we have some time, like 15 minutes. So you can ask. Otherwise, we can end the lecture. Can you deliberately tell me what do you mean by the case study? Yeah, I can upload this week for assignment paper here. If you want me to answer about the case study, then if I would like to know what do you exactly mean by the term case study? Okay, I have uploaded. Just wait. I'll share this assignment folder. Okay, the solving problems. So you can find out different gate questions which are related to this computer networks, and even not only that, you can also find out multiple books which are the corresponding book that is uh, we have seen here. Stop sharing. That the basic books that you use to see for in this computer networks. I'll just share the link. Yeah, you can refer Tenenbaum or this Andreas Tenenbaum that is mostly followed. From there, you can refer to the major questions which you want to solve. Yeah, this one exactly is the name Tenenbaum. Okay, so any further clarifications or any doubts? Okay, so we end the lecture here. I thank you for you all for attending. You can all you might leave.